Okay, we have here a pretty interesting integral from the UNSW Integration Bee from 2020. This was problem C3. We have the integral from -1 to 1, arctan of 2 to the x dx. Okay, now when I first did this, I thought I could finish it really quick because we have here, you'll notice we have bounds that are symmetric around 0. We've got an odd function, arctan. So when we have an odd function and symmetric bounds, just put down 0 and that's it. And this would be great, except it's completely and totally wrong. The reason it's wrong is because this is actually not an odd function with this input here. If it was just arctan of x, then we could put down 0 and that'd be true. But just notice if you plug minus x in for x, you don't get a minus sign to pull out. It just turns into 1 over 2x. So this is not odd. But that's okay because we got other ways to deal with this. So what I want to do is I'm going to do a u substitution and try to flip the bounds around. Just a very simple u substitution. If I call my u equal to minus x, we have x equals minus u, take a derivative, then dx is minus du. So we'll just go ahead with this. If you plug a 1 in here, we get minus 1. You plug minus 1, you get 1. So our bounds are flipped around. And this is going to turn into arctan. And then if we plug in minus u, we're going to end up, this is going to be 2 to the minus u. But I think I'm actually just going to write this as 1 over 2 to the u. And then our dx just becomes minus du. But I'm going to use the minus sign, bring it out front, and use to flip the bounds. So we'll just turn this to a plus, turn this to a minus, and then the bounds are back the way they were. But now, because what I'm planning to do is I want to add this to the original integral and see what happens. So I'm going to turn this, I want to change my variable back to x. It's a definite integral, so I can change the variable. So I'm just going to rewrite this and write the whole thing in x. And we'll just put a label on this. So the original integral, we'll call this thing I. And so this thing is I, and so this thing is also I. And then we'll just add this copy to this copy in order to have 2 copies of the integral, or 2i. And then let's see what we have. So the first one, we're going to have just arctan of 2 to the x. And then for the second one, we'll have this thing. But now at this point, hopefully this thing right here is kind of familiar. We can use an identity on this. So let me just write out the identity we can use for this thing. Okay, we have our identity over here to the right. I'm pretty sure I did a video on this. I also might have done, this is basically the same thing as arctan plus inverse cotangent equals pi over 2. I can't remember in one of the previous videos if I forgot this condition that x needs to be greater than 0. If x is less than 0, you end up with minus pi over 2. So when I did this the first time, I was scared for a moment because I noticed our bounds still go negative. And so I'm wondering, okay, is x greater than 0? But in this case, our x value is this input. So it's 2 to the x. If this is our input here, not x, if our input is 2 to the x, 2 to the minus 1 is just 1/2, which is still greater than 0. So what that tells me is we can use this. This whole thing is actually going to be pi over 2. And we're just going to integrate from -1 to 1 of pi over 2, which is a constant value. So coming down here to finish it off, we still have 2 copies of our integral. Integrating pi over 2 is going to be just pi over 2 times x. And we just need to evaluate this for -1 to 1. Plug in, plug in, plug in. So we're going to have pi over 2. We can just do it like this. 1 minus, evaluating -1. Minus times minus is plus. So this is going to be a 2 times pi over 2. So this is just pi. But then we need to remember that we have 2 copies over here. So I'll divide by 2, cancel that, divide by 2. And so for our final solution, we just have pi over 2. Okay, really good problem from UNSW 2020. Thanks everyone for watching. Have a good day.